You build a cutting-edge robotic exoskeleton, strap it to a paralyzed hand, and command it to pick up a glass of water. It moves perfectly, right up until it shatters the glass into 1,000 pieces. For a century, scientists designed prosthetics around mechanical strength. We perfected the motors, springs, and leverage, treating the human arm like a miniature construction crane. But that focus on movement ignored the body's most important feedback loop. Without a sense of touch, a patient is entirely blind to the amount of physical force they are actually exerting. All the physical movement in the world is useless if the biological sensory loop remains broken. Right now, more than 50 million people live with severe hand impairments, often caused by a stroke or a traumatic spinal cord injury. Strapping a motor to a paralyzed arm can force the fingers to move, but the result is usually the same. Patients struggle with the most basic daily tasks, like holding a paper cup, because the machine can't feel the object it's holding. Fixing a paralyzed hand requires a move away from pure mechanics. It requires a system that can bypass the injury and hack the nervous system to restore a sense of feeling. This is the Senso-Exo. It's a soft robotic glove integrated with a neuro-sleeve, a device that acts as a non-invasive wiretap on the human nervous system. The first part of the system is a module called Functional Electrical Stimulation, or FES. It's designed to provide the raw power needed to open and close paralyzed fingers. This diagram shows how FES shoots calculated electrical pulses directly into the forearm muscles. By doing this, the system bypasses the damaged brain and overrides muscle spasticity to manually trigger a contraction. This provides enough strength to lift heavy objects, but without a way to regulate that power, the movement remains clumsy. Generating electrical power in the muscles is only half of the equation. Without sensory data, the hand is still essentially moving in the dark. To solve that, researchers embedded tiny pressure sensors directly into the robotic fingertips of the glove. The moment those fingertips touch an object, the sensors calculate the exact amount of force being applied in real time. This visualization shows how a microcontroller translates that physical force into electrical signals. These signals are sent through the skin and into the patient's median and ulnar nerves using a method called TENS. These signals create a specific artificial sense of touch. The patient perceives a biological vibration in their own hand, exactly where the robot makes contact. By merging the machine sensors with the human nervous system, the patient regains their situational awareness. Scientists tested this on 14 patients with severe injuries. Some had no protective sensation at all. They couldn't feel a thing in their hands. They were tasked with a high-stakes challenge, picking up a virtual egg, calibrated to shatter if the grip exceeded 100 grams of force. When the patients used the robotic exoskeleton on its own, they couldn't tell how hard they were squeezing, and so they crushed the egg every single time. But as soon as the neuro-sleeve is activated, the nerves fire. The patients feel the artificial touch, realize they've made contact, and stop their grip just in time to hold the object safely. Restoring that single sense of touch turns a destructive machine into a tool capable of genuine dexterity. When researchers looked at the clinical data, they found something that seemed to contradict basic medical logic. In patients with central nervous system damage, the brain theoretically shouldn't be able to process any signals coming from the arm. The path is supposedly blocked. This neural map shows why that wasn't the case. Artificially stimulating the nerves routes signals through surviving peripheral pathways, circling around the damage to reach the brain. A heat map overlay reveals the result, restoring sensitivity to nearly half of the previously stone-numb hand. It proves the body's hardware isn't truly gone after an injury. It's just waiting for a piece of technology that can speak its language. This wearable, non-invasive sleeve produces results that once required high-risk brain implants and massive surgical costs. Early robotics attempted to solve hand impairment by trying to completely replace the human body with heavy, unfeeling machinery. Progress happens when we stop treating technology as a replacement for our limbs and start using it to translate the physical world into a dialect our nerves can understand. Centering the sense of touch provides the foundation for the next generation of paralysis treatment. Subscribe for more deep dives into the science hidden in plain sight.